Hello and welcome to The Explainer. Today, we are diving deep into an invisible battle that's happening all around us all the time. It happens whenever anything moves through a fluid, like a speck of dust floating in the air or a rock sinking in a lake. We're going to unpack the incredible physics of fluid drag.
So, let's start with a really simple question that you've probably asked yourself before. Why is it that a tiny, dense raindrop just plummets to the ground, but a big, delicate snowflake just sort of drifts down? I mean, they're both just water falling through the same air, right? Well, the answer is all about a fascinating tug-of-war between invisible forces.
All right, so here's our game plan. First, we'll follow a single particle as it starts to fall. Then we'll look at the forces battling it out. We'll see how it eventually hits a top speed, and then, this is the cool part, learn how we can actually predict that speed. And finally, we'll zoom out and see what happens when things get a little more complicated than just one perfect sphere.
Okay, let's set the stage. I want you to picture a single, perfectly round particle. It's just hanging out, suspended in a fluid. And on the count of 3, we let it go. And its journey begins right now.
You see, at the heart of this whole thing is a really simple conflict. The particle, thanks to gravity, wants to fall straight down. But the fluid that it's falling through, it's not having it. It pushes back, creating this resistance, this force that fights the particle's motion every single millimeter of the way.
So let's meet the two main players in this fight. In one corner, you have the force that's pulling the particle down, and in the other corner, you have the force that's pushing it right back up. This is the ultimate showdown, gravity versus drag.
Now let's peek behind the curtain at the forces themselves. The downward force, let's call it F1, is basically the particle's weight once you account for the fluid trying to make it float. And here's the thing, it depends on stuff like the particle's size and density, which don't change. So that downward pull is constant. But now look at the upward drag force, F2. It depends on a lot of the same stuff, but here's the kicker. It also depends on the particle's velocity, squared. And that is the secret. The faster the particle falls, the stronger that drag force becomes.
So why does this drag thing even happen? Well, this picture shows it perfectly. As the particle shoves its way through the fluid, it creates a high-pressure traffic jam at the front. And behind it, it leaves this messy, chaotic, low-pressure area called a wake. And that pressure difference literally sucks the particle backward. It's the exact same reason cyclists and race car drivers ride so close to each other. They're hiding in that low-pressure pocket, letting the person in front take the hit.
So it turns out this total drag force is really made of two different things. First, there's what we call skin friction. And it's exactly what it sounds like. It's just the fluid rubbing up against the particle's surface. And then second, you have form drag, which is that pressure difference we just talked about, caused by the particle's shape messing up the smooth flow of the fluid.
So our particle is falling, it's speeding up, and as it does, that drag force just keeps getting stronger and stronger and stronger. And eventually, something's got to give. And that brings us to the climax of our particle's big journey, the stalemate.
And this is it. This is the magic moment. The particle hits a very specific speed where that upward drag force has grown to be exactly, perfectly equal to the constant downward pull of gravity. The forces are balanced. The tug-of-war is a draw.
And this state of perfect balance defines a concept I'm sure you've heard of, terminal velocity. Because all the forces pushing and pulling on the particle now cancel each other out, the net force is 0. So it stops accelerating. It keeps falling, for sure, but now it falls at a steady, constant, maximum speed. That is its terminal velocity.
And the best part about physics is that we can actually calculate this. By taking our gravity force and setting it equal to our drag force, we can solve for that final speed, ut. And this equation tells us that the terminal velocity depends on stuff that makes sense, right? Like the particle's size, its density, the fluid's density, and this really important character, CD, the drag coefficient. We're going to need to figure that one out.
Okay, so we've got this great equation for terminal velocity, but there's a catch. It's got that one tricky variable in it, the drag coefficient, CD. And to figure that out, we first have to understand the actual character of the fluid flow. We need to know the rules of engagement.
So how in the world do we find that drag coefficient? Well, the key is a very special number called the Reynolds number. You can think of it like another tug-of-war, but this one is happening inside the fluid itself. It's a ratio of the fluid's tendency to just keep plowing ahead versus its own internal stickiness. And this one simple number tells us everything. It tells us if the flow around our particle is going to be smooth and orderly, what we call laminar, or totally chaotic and wild, which we call turbulent.
So you see, finding the terminal velocity isn't really a single calculation. It's more like a three-step recipe. First, you've got to calculate the Reynolds number for your particle. Then, based on that number, you figure out which flow regime you're in. And only then does that regime tell you exactly which formula you need to use for the drag. And this table just lays it all out for us. If your Reynolds number is super low, you're in that smooth laminar zone, and you use one formula. If it's in the middle, that's the intermediate zone with its own formula. But then check this out. If the Reynolds number is really high, you're in the chaotic, turbulent regime, and the drag coefficient just becomes a constant. It doesn't change anymore. Wild, right? Each regime really does have its own set of rules.
And this right here, this is a classic chart in fluid dynamics. It puts everything we just talked about into one picture. Along the bottom, you have the Reynolds number, going from smooth on the left to turbulent on the right. And on the side, you have the drag coefficient. See how the line starts out super steep on the left? That's our first regime. Then as you move to the right and things get more chaotic, the curve starts to flatten out until it becomes almost a perfectly flat line. It's the perfect visual roadmap for this whole process.
Okay, so up to this point, we've only been talking about one perfect, lonely little sphere. But let's be honest, the real world is a lot messier than that. So let's zoom out a bit and see how these ideas play out in a wider world.
For example, what happens if your particle isn't a perfect ball? What if it's shaped like a little cube or a flake, like our snowflake from the beginning? Well, it's okay. We've got a fix for that. We just plug a shape factor into our equations. And what if you have a whole cloud of particles all falling at once? Well, that's a whole different ballgame called hindered settling. Basically, the particles in the walls of the container all start to get in each other's way.
Yeah, there's a line from the source material that just sums this up perfectly. It says that the settling of one particle can be hindered by all the other particles and even by the walls of the container. In other words, as soon as you have a crowd, you can't just analyze one particle on its own anymore. The whole group dynamic completely changes the game.
So think about where we started, with a simple raindrop and a snowflake. But the principles we've just unpacked are, well, they're everywhere. This invisible battle between gravity and drag is absolutely critical for designing industrial separators, for medical tests that separate blood cells, and even for designing the heat shields that protect spacecraft when they come screaming back into Earth's atmosphere. It's amazing. So the final question is, now that you know what to look for, where else are you going to see this invisible battle at play?